Okay, we are continuing our development now of set theory. So doing an analysis of sets, let's remind ourselves of some of the basic things we talked about with sets last time. Last time we were largely focused on relations on sets. Remind me what a relation is.
Two-term predicate.
A two-term predicate. Remind me what a predicate is.
It's something that spits out true or false.
Yeah, it takes terms and it spits out true or false. True or false? 1 is less than 2.
True.
True. That's something you could call true or false. True or false? 1 plus 2.
Bad question.
Bad question. So last time we were talking about set operations. Things that when you look at, you can call true or false. Today we're going to be talking about set operations, like plus. Things that operation on the numbers takes numbers and spits out numbers. We're going to look at set operations are going to take sets and spit out sets. So last time we looked at these things. These are things that we can call true or false. This time we're going to be looking at set operations, things that take sets and spit out sets. So remind ourselves of some of the basic relations we talked about last time. So you had that, how do we read that? X is in set A. X is in set A. That's something you could call true or false. If I were to write this, 1 is in the set 1, 2. In that case, it's true.
Yeah.
If I were to write 7 is in the set 1, 2, in that case, it's false. So this was something you called true or false. We talked about what it meant for A to be a subset of set B. What does it mean for one set to be a subset of the other set?
Everything in the first set is.
Everything in the first set is also in the second set. This class is a subset of choir. Everyone in here is also in choir. Choir is not a subset of this class. Not everyone who takes choir is also in this class. Subset. So here's its definition. What does it mean for A to be a subset of B? It means if X is in A, then X is in B. That's how you read that. Giving you nice, dense notation now so you don't have to memorize whole paragraphs. Here's the definition of what it means for A to be a subset of B. It means if X is in A, then X is in B. What does it mean for this class to be a subset of choir? It means if you're in this class, then you're in choir. That's what it means for this class to be a subset of choir. Make sense? Now, what does it mean for two sets to be equal? That means that they have the exact same elements. So, a set A is equal to a set B if A is a subset of B and B is a subset of A. If everything that's in A is in B and everything that's in B is in A, then the two sets are identical. They're equal. That make sense? And then finally, we didn't really talk about this one, but just because it's common notation, introduce it to you. So our subset symbol, notice it has this underline. There's what we call a proper subset. A proper subset means A is a subset of B and A is not equal to B. We sometimes think about subset as less than or equal to, and proper subset is kind of like less than. They can't be the same set. They can't be equal to each other. So that's the difference between a proper subset and a subset. A subset, they can be equal to each other. A set is always a subset of itself. A proper subset is never, a set is never a proper subset of itself. That make sense?
Yep.
Okay, so with that, let's get now into our first set operations. So no longer set relations. We're not talking about things that return true or false. We're now talking about set operations. We're going to take sets and combine them in some way to spit out a new set. The same way that operations, plus, subtraction, multiplication, division, these take numbers and spit out numbers. We're going to look at operations that take sets and spit out sets. So the first set operation that we're going to look at is called set intersection. A, and that upside down U means intersect B. By definition, what do we mean by A intersect B? That is defined to be the set of all X where X is in A and X is in B. It's a set of everything in A and B. If we draw a little Venn diagram here, here's A, here's set B. What's everything in A and B?
The middle part.
That's this part right here. So if this is set A and this is set B, this part right here is set A intersect B. It's a set of all X where X is in A and X is in B. This point right here is in both A and B, so it's in the intersection. This point is not in both A and B, so that is not part of our intersection. Make sense? Okay. Now, flip your U over. We call that union. A union B is a set of all x such that x is in A or x is in B. It's everything that's in A or B. Is this point in A or B? Yes, so that would be included. Is this point? Yes. Is this point?
Yep.
Yes. So the union is the whole both sets, everything that shows up in either set. That's A union B, pictorially. With me so far?
So it can include both.
If it shows up in one or the other, it shows up in the union.
Including everything that shows up in both.
Yes. Yes. Remember, in order for or to be true, or means at least one of them. Alpha or beta is true when both alpha and beta are true.
Okay, yeah.
Okay. Set difference. A minus B. This is not subtraction on the real numbers. This is subtraction of sets. This is defined to be the set of all x, where x is in A and x is not in B. What does that mean in a Venn diagram? Here's A, here's B. We want A minus B. We want everything that's in A that's not in B. Is this in A and not in B? No. Is this in A and not in B? No. Is this in A and not in B? Yes. So it's this, if we were to color it in. That is A minus B. Notice that that is very different. A minus B is very different from B minus A. What would B minus A be? That would be everything in B that's not in A. That would have been the points over here. So A intersect B is the same thing as B intersect A. If it's in A and B, it's in B and A. A union B was the same thing as B union A. A or B is the same thing as B or A. But A minus B is very different from B minus A. So this is our first one that is not commutative. The order matters. In union and intersection, the order did not matter. With me so far? Okay. Now our next one is called a symmetric difference. And it's that little triangle symbol. Sorry, it's kind of close to my underline. It's a little triangle that we call delta B. And then the underline is just letting me know I'm defining something new. So A delta B, what is that? That's A minus B union B minus A. Let's draw that out in the picture. A, B. I want everything that's in A minus B or in B minus A. So where is A minus B?
It's everything on the left.
A minus B is this left-hand portion, right?
Right.
Here's A minus B. Now I need to union that with B minus A, which is over here. So it's everything except the middle part.
Okay.
And you see the symmetry to it? That's why it's called a symmetric difference. So A delta B, the symmetric difference, is A minus B union B minus A. This is the least used of these operations. These two are the most commonly used. Good so far? So we did it with a Venn diagram picture. Now let's do it in a concrete case where rather than giving you pictures of sets, I tell you exactly what the elements of the sets are. And you're going to calculate the union, the intersection, the difference, and the symmetric difference. So let's get started. A now is a set 1, 2, 3, 4. B is a set 1, 4, 7, 11. So there's our two sets. First thing we're going to do is calculate the union of A and B. We want everything that shows up in A or in B. So what shows up in A or B?
1,
1 does.
2,
2.
3, 4, 7, 11.
Perfect. Those are all the elements that show up in A or in B. If it shows up in at least one of them, it shows up in the union. Okay, what about the intersection? This is everything that shows up in A and in B. 1 and 4. Anything else? What are we missing?
The empty set, I guess.
The empty set doesn't show up in either of those.
No, you're right. So 1 of 4.
We're not missing anything. Good. All right. What is A minus B? It's everything that's in A that's not in B.
3 and 4.
Or sorry.
Oh no, 2 and 3.
2 and 3. There you go. 2 and 3. These are the only two things that show up in this set and don't show up in that set. And then finally, we have the symmetric difference. I want everything that's in A and not in B, together with everything that's in B and not in A. So what are all the things in A and not in B?
2, 3, 7, 11.
Well, let's start with everything in A that's not in B.
2 and 3.
That's 2 and 3. Now we need everything in B that's not in A. 7 and 11. Perfect. So we've done these out pictorially, shown you the Venn diagram model, and done it out with the concrete case. Here's exactly what the elements of the set are. Pretty straightforward? Okay. Now, basic theorem. So theorem 12.3 tells us all these 7 properties. Let's go through each of them, make sure that they make sense. The first one says that A union B is the same thing as B union A. If I take everything that's in A or B, which would be basically everything, that's the exact same thing as taking everything that's in B or A. Makes no difference. Similarly, everything that's in A and B is the same thing as everything that's in B and A. Makes no difference. Those two good? All right. Now for the next one, we need a C as well. So now we have 3 sets. This says if I union B and C first, so take everything that shows up in one of those, and then union A, that's the exact same thing as taking the union of A and B first, and then unioning C. Doesn't matter what order I do it, eventually I get everything in all 3 sets. That's what this says. You can union those 2 first, and then union with A, and that's the exact same thing as unioning those 2 first, and then unioning with C. Doesn't matter. That's what we call associativity. You know the same thing for addition. When I do 1 plus 2 plus 3, what do I add first? Those 2 or those 2? It doesn't matter. That's the same thing with union. You're unioning 3 sets together. It doesn't matter what order you do it in, you get the same result. That's what that's saying. Similarly, for intersection. Everything that's in B and C, let's see, everything that's in B and C, so far that's right here. Everything that's in B and C, and in A, that leaves us just this piece, so we were ultimately left with just that, is the exact same thing as first take everything that's in A and B would have been this piece right here, and then intersect that with C. Once again, leaves me just that piece. So it doesn't matter if I intersect those 2 first, and then intersect with A, versus if I intersect A and B first, and then intersect with C. We end up with the exact same set, just that very middle piece. All the things that are in A and B and C. Good? Okay, next. I take A and I union it with the empty set. So I want everything that's in A or the empty set. Let's try out a picture of this. Here's my set A. What's everything that's in A or the empty set? It's just everything that's in A. But I need to include everything in the empty set as well. Well, here's everything in the empty set. I can even juggle it. There you go. So we included everything in the empty set. So A union the empty set is just A. Unioning with the empty set doesn't change anything. It's like adding 0. Take A and add on 0 elements, and what do you get? A. Good? Now, A intersect the empty set. What does this say? I want everything that's in A and in the empty set.
Which is nothing.
Nothing is in both A and the empty set. So what's the set of nothing?
Next set.
The empty set. This is a set of everything that's in there or there. Remember that this is just shorthand for the set that looks like this. Now, I hate drawing the squigglies, which is why I do it. Just a set with nothing in it. Completely empty inside. That's what that symbol means. Empty set. That's just very annoying to write, so we have our shorthand. Good? Okay. Now, we get down to our 2 more interesting ones, which is how you distribute a union over an intersection, and how you distribute an intersection over a union. So if I have A union, B intersect C, that's the same thing as A union B intersect A union C. Let's make sense of this with the Venn diagram. Try and make it appeal to our intuition some. So here's A, here's B, here's C. Let's look at the left-hand side. I want everything that's in A, or it's in B and C. So A is all of A, And then B and C is this piece right here. So you see what that colors in? Now let's do the exact same thing. Sorry, I'm going to have to draw a bit smaller so that we have enough space. Looking at the right-hand side this time. So once again, here's A, here's B, here's C. This time, I want everything that's in A union B and in A union C. So A union B, that's all of A and all of B. And A union C, that's all of A and all of C. So what shows up in A and B together, as well as A and C together?
Everything that's in.
All of A does, and then this piece as well. That's everything that's in A union B, those two circles, and in A union C, those two circles. Make sense? Mm-hmm. And see how those are the exact same picture? Mm-hmm. Intuitively, this, well, we'll see it when we do the proof. And then finally, same thing for the intersection. With the intersection here, A intersect B union C is the same thing as A intersect B union together with A intersect C. So once again, let's draw out some Venn diagrams to make sense of this. Try and get to appeal to our intuition. Here's A, here's B, here's C. So I want everything that's in A and B union C. So we have to include A, but it also needs to be in B union C. So that's going to be this piece right here. That's everything that's in A and B or C. Make sense? Mm-hmm. Let's draw out the same picture now for the right-hand side. So here's A, here's B, here's C. We want everything that's in A and B. So A and B, where do they intersect? They intersect right here. A and B, or A and C. A intersects C. A intersects C, that's everything right here. And so we colored in the exact same portion. So there's pictorially trying to get intuition for it. Okay, so now I'm going to fly through a proof of one of each of these combinations. So I'll prove one of those two, one of those two, one of those two, one of those two, whichever ones you guys want. And I'm just going to do the quick algebraic proof. I'm going to be lazy, not including all the words. Okay, so which one should we do? Union or intersection up here?
Intersection.
Intersection. Okay, so I'm going to prove A intersect B is equal to B intersect A. Good? Okay, so let's do the proof. So B intersect, start with A intersect B, left-hand side. A intersect B is equal to, by definition, what is A intersect B?
Set X such that.
It's a set of all X, where X is in A and X is in B.
Mm-hmm.
So this is equal to, by definition, the set of all X such that X is in A and X is in B. With me? Mm-hmm. Now, we could go back to our truth tables. If we did a truth table for alpha and beta, we would see that alpha and beta is the exact same thing as beta and alpha. If we filled out our truth table, these two columns would have the exact same thing.
Yeah.
What that means is you can flip the order that you end in and it doesn't change anything. Mm-hmm. So if you don't believe me, the way you would test that is really quick with the truth table. I think that truth table is simple enough you could all do it easily.
Yeah.
So we won't write it out. And so this is the exact same thing as a set of all X such that X is in B and X is in A. X is in A. What is that?
All the numbers are in there.
Well, X is in A. It's something that returns either true or false. So this is just something that's true or false. This is just something that's true or false. We're just ANDing together two things that are true or false.
Okay.
Swapping the order that you AND two things together in is perfectly legal.
Yeah.
So this is like our alpha, this is like our beta. We had alpha and beta, and we swapped it for beta and alpha. That's all we did. Okay, and by definition, what is this? This is a set of all X where X is in A and X is in B. That's the exact definition of B intersect A. By definition, B intersect A is a set of all X where X is in B and X is in A. So, since AND is commutative, intersection is commutative. If we were proving this one with unions, Replace your intersections with unions and all your ands with ors, and it's identical. Since union is defined in terms of or, since or is commutative, union is commutative. Since intersection is defined in terms of and, since and is commutative, you can swap sides, then intersection is commutative. Make sense?
Yep.
Okay, so next one, let's do a union this time since we did an intersection on that one. So out of 3 and 4, oh, I guess they have both, so pick whichever one you want, 3 or 4.
Say 3.
3. Okay, so on 3 we're looking at A union, B oh, sorry, they didn't have both. All right, but it doesn't matter. Okay, so there's what we're looking at. Now remember, union is
It's an operation.
it's an operation. When I take B and I union it with C, what does it give me?
What's that?
Just a set. So I have a set union together with a set. This is just a set, whatever it returns. So by definition, what is A union this set? It's a set of all x such that x is in A or x is in whatever that other set is. In this case, B union C. The fact that we wrote a set as a bigger combination of letters, bigger combination of symbols, doesn't change the fact that it's a set. So by definition, what is a union of two sets? It's a set of all x where x is in the first set or x is in the second set. This is a set of all x where x is in the first set or x is in the second set. Now, what did it mean for x to be in B union C?
Okay, can it be an A?
Well, just its exact definition. So this is a set of all x in A, or let's look at exactly what this piece means. If x is in B union C, that simply means x is in B or x is in C. Just now unraveling that definition. There we go. So I unraveled this union to get to here. Now I unraveled that union to get to here. Just the exact definition. What does it mean for x to be in B union C? It means x is in B or x is in C. That's what it means for x to be in B union C. So that's exactly what it means. Now notice what I have. I have alpha or beta or gamma. Right here, just re-symbolizing it, this is the same thing as alpha or beta or, what do you guys use to as a third one? You okay with gamma? And you could do your truth table to prove that that is the exact same thing as alpha or beta or gamma. Sorry, no other parentheses. These two things are the exact same thing. When you're ORing, you can shift your parentheses. ORing is associative. That was one of your homework problems for the discrete math kids going forward back. I don't know if you geometry kids saw that as one of your logic problems. Probably in one of your tables there. But those are the exact same thing. You don't believe it, quickly write out a truth table and they'll give you the exact same columns. So we can simply move those parentheses and we're not cheating because we have alpha or beta or gamma. Just move the parentheses. Perfectly legal. ORing is associative. And so this gives me the set of all x such that x is in A or x is in B, put those together in our parentheses, or x is in C. Now, what does it mean to say the set of all x, what does it mean to say the set of all x where x is in A or x is in B?
A union B.
That's the definition of the union. So this is the exact same thing as a set of all x such that x is in A union B or x is in C.
Good morning.
Good morning.
This is a cool class. Look how many students are here.
Yeah, I got popular for a few weeks.
You sure did. Is anybody gone?
I don't know.
Is anybody missing a friend today? You guys?
Olivia's gone.
Oh yeah,
Olivia?
Olivia. She sent me a message.
Okay. Thank you so much. Have a nice day.
You too.
Hi.
Okay. So now we have the set of all x where x is in this set or x is in this set. Once again, by definition, that's the definition of A union B together with the union of C. What is this by definition? It's a set of all x such that x is in the first set or x is in the second set. Make sense? And so once again, union is associative simply because OR is associative. And if we want to do the proof with intersection, flip all your unions with intersections and flip out all your ors with ands. And it's the exact same proof. Since and is associative, intersection is associative. Okay, on to the next one. 5. Should we do the left-hand side or the right-hand side?
Right.
The right-hand side. Okay, so let's look at A intersect the empty set. By definition, what is this equal to?
The empty set.
No, by definition, you don't get to just
Equal to A.
let your intuition tell you what it is. You need to go look exactly at the definition. What does it mean to do A intersect some other set? A intersect a set, by definition, is a set of all x, where x is in the first set and x is in the second set.
Okay.
So by definition, here's its exact definition. It's a set of all x, such that x is in A, and x is in the empty set. Right?
Mm-hmm.
And now, x is in the empty set is always
Nothing.
False.
false. Remember, this has to be true or false.
Mm-hmm.
X in the empty set is always
False.
false. So this is the exact same thing as a set of all x, such that x is in A and false. If you and together with a false, you always get
False.
false. So this is a set of all x, such that false. We never satisfy the condition. I want all the x that satisfy this condition. False. How do you satisfy false? How do you make it true? You can't make false true. So this is simply just the empty set. Those are all the x that satisfy
Nothing. Okay, that's cool. Right.
a false condition.
Cool.
And I don't know if you guys did the truth table with that. I think you did. You showed that alpha and false is always equal to false. And you did alpha or true is always equal to true. Okay, so there's that one. This one, very simple. Okay, now 6 or 7.
7.
What's that?
7.
7. All right, let's look at 7. For 7, we have A intersect B union C. What is that equal to? By definition, this is equal to the set of all x, such that x is in the first set, and x is in the second set, B union C. Okay, now we need to unravel that B union C. So this is equal to the set of all x, such that x is in A, x is in A and parenthesis. What it means to be for x to be in B union C?
X is in either B or C.
X is in B or x is in C. Good. Okay. Now we have to use one of your distribution rules.
Distributing an and over an or.
Yeah, distributing an and over an or. So going back to your truth tables, you showed that alpha and beta or gamma is the same thing as alpha and beta or alpha and gamma. So you would need to prove in your truth tables that these are identical. I can't remember if that's one that we actually did in class and wasn't even a homework one.
It was.
I know we distributed the not, can't remember if we distributed the and. But, so now, that's how we distribute an and over an or. That's what we have here. We have alpha and beta or gamma. We just have a statement and a statement or a statement, well, predicates, but things that return true or false. Okay, so that's the exact same thing as this. So I can rewrite that, give me a little bit more vertical space. I can rewrite that as a set of all x, such that we have alpha and beta, x in A and x in B, or alpha and gamma, x in A and x in C. Just using our distribution from our propositional logic. And now finally, let's plug in some definitions. What does it mean to look at the x in A and in B? What's that the definition of?
The intersection.
The set of all x in A and in B. That's exactly what we mean by the intersection. It's the set of all x where x is in A and x is in B. So this is equal to the set of all x such that this one turns into x in A intersect B. And we're going to OR that with this one turns into x in A intersect C. Now finally, what does it mean? All the x where x is in the first set or x is in the second set.
Union.
That's the definition of the union. If it's in this set or it's in this set, it's in the union of those two sets. If x is in this set or x is in this set, it's in the union of those two sets. So this is exactly what's meant by A intersect B, the first set, union together with A intersect C, the second set. Once again, to prove whichever one we didn't do 6. To prove 6, just flip all your ands with ors and all your intersections with unions. Just swap them all out. And it's the exact same proof. Good? Mm-hmm. Okay. Now to some counting. Let's see. What would be the best way to introduce this to you? Let's say that I wanted to count how many people were in trig or physics. How would I do that?
Made both sets and gone.
Let's say that I know that there was 10 people in trig and 5 people in physics. How do I count how many people are in trig or physics?
You count.
Add them.
Count, you add them together.
There's just 15, right?
Yeah.
What if Bob's in both?
Oh.
Well, then there's 14.
Well, then there's 14. What if Bob and Shirley are in both? So you don't have enough information just knowing how many people are in each class to figure out how many people are in either class, right?
Yeah.
You also need to know how many people are in both. So you would say 10 plus 15, but now I need to subtract away however many people are in both.
Or the intersection of both of them.
So what we're saying is, let's say that A is everyone in physics, and B is everyone in trig. So you're saying to get how many are in physics or trig, you count how many are in physics. Remember that absolute value just means however many things are in there. So A here is going to be the set of the 10 people taking trig or whatever. This is then going to be the actual number 10. It's just however many things are in A.
Yeah.
Plus, however many people are in physics. And then we need to subtract
How many are in both?
how many are in both. So we need to subtract how many are in what set?
See,
The intersection of A, B.
The intersection of A and B. What's the intersection of A and B? It's everyone in both. And this will tell us how many are in either. That will tell us the size of A union B.
Okay.
You follow that in your intuition?
Yeah.
Now here's what we're going to prove. I'm going to prove a slightly different version of it. I'm going to move this piece to the other side by adding this to both sides. So I'm going to add that to both sides, and here it is. That's what we're proving. Everyone see how this is written up right here? So if A and B are sets, then the size of A plus the size of B is equal to the size of A union B minus the intersection.
But if it's set, doesn't that mean that all the duplicates are already taken out of the intersection?
But here you're double counting, just like you did.
Oh.
So here you're double counting, here you get all of them, now you need to get rid of the overlap. That's why I think it's easier to put that on the other side when you're first thinking about it, which is the way I present it to you here. I think it helps the intuition better. Because this you only want to count each person once, which is a better intuition. Okay, so let's jump into that proof. If A and B are sets, then the size of A plus the size of B is equal to the size of A union B minus the size of A intersect B. Let's see it in just one more concrete example before we go through the proof. Have it written out down here. So here's your trig students, here's your physics students, or whatever we said before. So let's write out that exact formula and see how it makes sense. How many people are in A? What's the size of A?
6.
6. Plus, what's the size of B?
5.
5. Notice that in counting them, we counted these middle dots twice.
Yeah.
So 6 plus 5, that counts all of them, counting the middle twice, is equal to, what's the union? How many are in A or B?
11.
You guys can count. How many dots are there in A or B?
8.
Do I need to bring my child in here? 1,
9.
2.
9.
Holy cow! Someone can count dots. They're right there. Okay. There's 9 dots on the board. And now we need to, you guys, you let me do that. It's plus, because it was minus over here.
Yeah.
Plus over there. Nobody caught that. I did that on purpose. Just to test you. So now we have 9, and now we need a plus the intersection. How many are in both?
2.
2. So when we count 6 plus 5, we count those middle dots twice. So that's the same as counting all the dots, and then counting the middle dots again.
Yeah.
So count everything in A,
11.
plus everything in B. That gives you everything in A or B, plus everything in both.
Yeah.
Because when you count up everything in A plus everything in B, you count the middle twice.
Yeah.
So that's the same as counting all of them and then counting the middle again. Everyone follow that?
Yes.
Okay, so we're just going to give a quick counting proof of this. Let A and B be sets, and assign the label X to every element in A, and Y to every element in B. Just labeling them. So here's an element in A. I give you an X. 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 And everything in Y, or sorry, and everything in B, I give you a Y. You get a Y. You get a Y. You get a Y. Oprah over here. You get a Y. You get a Y. Okay. So there we go. We gave everything a label. It remains to show that the size of A plus the size of B and the size of A union B plus the size of A intersect B count our labels. If this and this count the exact same thing, then they're equal. Observe that we assigned the size of A x's. We assigned an x to everything in A. So how many x's did we assign? However many things are in A, that's how many x's we assigned.
Yeah.
And we assigned the size of B y's because we gave a y to everything in B.
Yeah.
So for a total of the size of A plus the size of B, that's how many labels we gave out here. If we count our labels, we gave out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 total labels. Good so far? Now, observe that we assigned at least one label to everything in A union B.
Yeah.
Everything in A or B got at least one label. And we assigned one more to everything in A intersect B. Everything in A intersect B got 2 labels. So count all our ones that have one label. And now we need to count again for the ones that got a double label. So A union B counts everything that got at least one label. And A intersect B counts the things that got a second label. So since the size of A plus the size of B and the size of A union B plus the size of A intersect B count the same thing, then they're equal. Counting proof. Any questions on that? Hopefully pretty intuitive one. Let's quickly put this to use to see how you can look impressive counting things that might at first glance seem kind of hard to count. So here's what we're going to do. You're going to tell me how many integers in the range from 1 to 1,000 are divisible by 2 or 5. 5 really loud. 2 or 5? Question mark. Not exclamation point. Okay. How many integers in the range of 1 to 1,000 are divisible by 2 or 5? 500?
More than that.
More than that? How many is it?
You're right, it is
7.
700?
Balls. Everything is.
Let's calculate it. And now you don't have to guess. So let's first let A be the set of everything divisible by 2, and B be the set of everything divisible by 5.
Okay.
So how many integers between 1 and 1,000 are divisible by 2?
500.
500. How did you come up with that so quick?
Because one's on.
All the evens are divisible by 2. 1, no. 2, yes. 3, no. 4, yes.
Yeah.
5, no. 6, yes.
Yeah.
Half your integers are divisible by 2. Okay, so there's 500 of these. Okay, how many are divisible by 5?
200.
200. How did he come up with that? Every fifth one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Every fifth element is divisible by 5.
Yeah.
What are the odds? Okay, so our size of A is, guess I wrote space here, 500. Our size of B is 200, which is how we got 700. You forgot to remove now the intersection. What's A intersect B? What does it mean for you to be in A and B? It means you're divisible by 2 and 5. If you're divisible by 2 and 5, you're divisible by 10,
Yeah.
right?
Yes.
So then how many numbers are divisible by 10?
100.
100. So now, plugging in our formula, how many are in A or B? Well, it's the size of A plus the size of B minus the intersection. That's 500 plus 200 minus 100 gives us 600.
Yeah.
And there you go. So you kind of struggle thinking about it, let appeal to your intuition. Easy counting.
Yeah.
And that is a very common mistake, is to forget to subtract the intersection. It's what you guys did right at the beginning when I said how many people, if 10 are in physics and 5 are in trig, how many are in physics or trig? And you all said 15.
No.
Oh, and then when we had our picture here, you struggled to count dots. Okay, so now, basic definition, pretty simple one. Sets A and B are disjoint, provided that A intersect B is the empty set. All this means is they have nothing in common, right? So, I don't know, what's a good senior elective that people do? What's a creative one? Probably some art course. Odds are that art course and my calculus class don't have any students in common, right? Probably very different types of kids. That's what we mean by their disjoint. Their intersection is empty. No one is in both.
Yeah.
That's it. Straightforward?
Yeah.
So what does it mean for two sets to be disjoint?
Means they don't have any intersection.
Their intersection is empty. They don't share any elements, however you want to say it. Their intersection is the empty set is the definition, but however you want to say it, all logically equivalent. All right, question. Here's set A, here's a set B. Are those disjoint?
No.
But this has elements that don't show up in here, and this has elements that don't show up in there.
Yeah, but it has an element.
What on God's green earth does that have to do with anything? The question was, do they share an element?
Yes, 3.
3. So they're not disjoint. If I got rid of if I made that 3 a 13, well, 3 is still part of 13, so they still share an element, right? Not by a mile.
Okay.
That's a bunch of nonsense. 13 and 3 are very different. Those are now disjoint sets. They have nothing in common. Okay. Now we're going to expand it. We want to talk about what if we have multiple sets, and we don't want to say any, and we want to say none of those sets share anything in common.
Okay.
What if it happened to be the case that when you look at trig, physics, biology, and chemistry, there was no one that showed up in more than one of those classes. So they were all disjoint no matter how you take combinations of them.
Yeah.
That's what pairwise disjoint here is going to mean. So the sets A1, A2, AN, however many you want to talk about, could be 5, could be 10, could be 2. We call them pairwise disjoint, provided that if you pick any two sets, they're disjoint.
Yeah.
Pick any two sets, they don't have any elements in common. That's what this is going to say in dense notation. So it's a simple concept, but the notation is dense. Odds are you aren't used to big boy notation. So let's try to wrap our heads around it. So we call them pairwise disjoint, provided that A sub I intersect A sub j is the empty set for all I and j between 1 and n, where I is always a number different from j.
Yeah.
So here's a concrete case, and let's make sense of that definition. I'm going to call A1 the set 1, 2, 3. A2, 4, 5, 6. A3, 7. A4, SpongeBob star triangle. A5, 8, 9, 10, 11, 12. Okay, there's 5 sets. With me so far? Now, do any of those two sets share an element with any other set? That's intuitively what pairwise disjoint means. Now, I'm trying to give you intuition for how this says the same thing.
Okay.
So here's all you do. Give me an I between 1 and n. In our case, n is 5. We have 1, 2, all the way up to a sub 5. So give me an I between 1 and, well, 4. 3. Now, pick any j greater than I, but still less than or equal to our n.
SpongeBob.
4.
It has to be a number. A number.
7.
I and j are numbers. So now in our concrete case, we have 1 is less than or equal to I, is less than j, is less than or equal to 5. So I need you to give me two numbers, I and j, where I is less than j, and they're sandwiched between 1 and 5. So any two numbers, that satisfies this. So j can be 3, or I can be 3, but now j has to be either 4 or 5. Pick 4. We'll say j4. What does that mean? Look at a sub I, or in other words, a sub 3, and look at a sub j, or a sub 4. What's the intersection of these two sets?
None.
Nothing, or the empty set. So the intersection of a sub I and a sub j is the empty set. Now repeat the process. Pick any I and any j you want, as long as they're sandwiched this way. I could have picked I to be 1 and j to be 5. A sub 1, a sub 5, take their intersection. What is it?
Nothing.
The empty set. Repeat again. So do this for any possible combination of I and j sandwiched this way, and their intersection better come out the empty set. That's what it means for them to be pairwise disjoint. If there's a single case where this doesn't work, then they're not pairwise disjoint. If I would have added to a sub I now 1, these are no longer pairwise disjoint. Because I was able to find some I and j that made this false. Namely, I equal to 1 and j equal to 5. The intersection of these two is no longer the empty set. Very dense notation, but the concept is pretty straightforward. Trying to, especially for my discrete math kids, get you comfortable with dense notation because it just gets denser as we go. You geometry kids, you'll be better off. Okay, so that's what that means. There's our examples. Quick proof. Okay, if A and B are disjoint sets now, so let's say A's here and B's here. They have no points in common. Then how can I figure out the size of A union B?
The size of A, the size of B.
Just add the two sizes together now. So when there is no overlap, then the size of A union B is simply the size of A plus the size of B. That's all we're proving. Okay, so if A and B are disjoint, they have no elements in common, they have no intersection, their intersection is empty, then the size of A union B is equal to the size of A plus the size of B. That's what we're proving. Okay, let A and B be disjoint sets, and observe A intersect B is equal to, if A and B are disjoint, where is their intersection? I'll show it to you. Want to see it again?
Yeah.
Here it is. That's their intersection. They don't have one.
Yeah.
So they don't have an intersection. So what's the set of everything in both of them? It's the empty set. Perfect. So then we know, we proved over here, or over here, that the size of A union B is equal to the size of A plus the size of B minus their intersection. Which is equal to the size of A plus the size of B minus the size of their intersection. What's the size of the empty set?
Empty set. It's not zero.
How many things are in there?
Nothing.
Zero.
How many things are in there?
Zero.
I'm not saying what's in there. What's in there? Nothing. How many? 0. 0 counts nothing. Okay. Which is equal to, obviously, the size of A plus the size of B. If we want one more line there, we're done. Okay. That's all there was to that proof. Good? All right. Last operation that we're going to define on sets. It's called their cross product. Let me erase that last line of the proof so it doesn't make it hard to read. Okay. The cross product now of two sets A and B. By definition, it is the set of all ordered pairs where the first element comes from the first set, and the second element comes from the second set.
Okay.
Let's write this out very concretely. I have the set of all, or I let A be the set 1, 2, 3, 4. And I let B be the set A, B, C. Now I'm looking for the cross product of A and B. It's a set of all ordered pairs where the first element comes from your first set A, and your second element comes from your second set B. So 1A, 1B, 1C. That's all the things 1 can be paired with.
Yeah.
2A, 2B, 2C. That's all the things 2 can be paired with from that set. 3A, 3B, 3C, 4A, 4B, 4C. Question, how many things are in the cross product here? For each of these 4 objects, I paired them with 3 things.
12, yeah, so 12.
So how many in the cross product?
12.
12. I had 1 paired with 3 things. 2 paired with 3 things. 3 paired with 3 things. 4 paired with 3 things.
Times 4 is.
I had 3 4 times for a total of 12. 3 times 4 is 12. All sorts of fancy math. Okay, now let's look at B cross A. Very different. What is B cross A? It's a set of all the ordered pairs where the first thing comes from this set.
Yeah.
So now my first elements have to come from B, and my second elements have to come from A. So A1, A2, A3, A4, B1, B2, B3, B4, C1, C2, C3, C4. Now notice how these 2 are different in size. Yeah, they're not different in size.
Yeah.
Okay. All these elements are the exact same as all these elements, except for swap the order.
Yeah.
That's the only difference. So A cross B is not the same thing as B cross A. So here's your second operation that is not commutative. Good. All right, as one of your homework problems, you will prove, in fact, that the size of A cross B is just equal to the size of A times the size of B. Not for geometry. You guys won't have to do any counting proofs. Okay. Now, lastly, De Morgan's. De Morgan's law for sets. If A, B, and C are sets, then A minus B union C is the same thing as A minus B intersected together with A minus C. And A minus B intersect C is the same thing as A minus B union A minus C. It tells you how to distribute a minus over an or. When you distribute, over a union. When you distribute a minus over a union, it flips it to an intersection. And when you distribute a minus over an intersection, it flips it to a union. I'm only going to prove one. The other way that you prove this is almost identical. So, going over the exact proof. So I'm going to do this one. A minus B union C. By definition, what is that? What does it mean to do a set minus a set? It's everything that's in the first set and not in the second set. That's what A minus B is. It's a set of everything in A that's not in B. So that's a set of all X where X is in A and X is not in B union C. Another way that we could write this is a set of all X such that X is in A and it is not the case that X is in B union C. Not sure if one of those helps you see it better than the other, but that's what it says. Okay. What does it mean to say that X is not in B union C? Or what does it mean to say it is not the case that X is in B union C?
X is not in B or X is not in C.
Yeah, that it is not the case that X is in B or X is in C. We do not have X in B union C. It is not the case that X is in B or X is in C. You see going from here to here? Okay, now we already learned how to distribute a not over an or. When you distribute a not over an or, it turns it into a and. So, distribute the not over the or, and we get X is in A and, same and there. But when we distribute that in, you negate that, and switch your or to an and. So X in B, the negation of that is X not in B. Flip your or to an and the negation of X in C is X is not in C. Okay? So, next thing we got to do is we just distribute an and over an and. You can do that however you want. So I know X is in A and X is not in B and X is not in C. That's the same thing as X is in A and X is not in B. Together with X is in A and X is not in C. Good? Alright, what does it mean for X to be in A and X to not be in B? What's that the definition of?
A minus B.
If it's in A and not in B, that's exactly what we mean by x is in A minus B. And if x is in A and x is not in C, that's exactly what we mean by A minus C. So therefore, we have x is in A minus B and x is in A minus C. Or in other words, we have A minus B intersected together with A minus C. And for this one, the second one, the exact same thing, just flip your ands with ors. And your ors with ands. It's identical. So it's called De Morgan's because, I didn't tell you this when we did it because I always forget which one De Morgan's is. You learned back when we were doing propositional logic, not alpha and beta is the exact same thing as not alpha or not beta. And same thing when you swap your ors and your ands. So that was the logic, that was the crux of the proof here. So that's called De Morgan's in propositional logic. This is called De Morgan's in set theory because it hinges on the same piece of logic. So you notice how closely related set theory and logic are. All these set theoretical things we were talking about, we always have them defined just in terms of brute force propositional logic. That's why you need logic to construct set theory and why it's at the foundation of pretty much everything. Okay, so for you geometry students, go ahead and take a break. And for you other students, we get to the hard part. All right, I think that pretty much has it all. Okay, so our next section, section 13 or 12, can't remember, 12.
Actually, that was 12.
13, section 13. All it is doing is giving you two examples of combinatorial proofs, counting proofs. And it's just giving you completely spelled out examples of how to do two problems. That's all it's doing. Now they're tough problems. Counting proofs are in general hard. It's difficult for us to do them. So the author takes a whole section just trying to walk you through two of those problems. I'm going to walk you through what I think is the harder of the two problems, and then try and quickly explain to you the second one in a way that hopefully makes what you read from the author make perfect sense. Okay, so the first one that we are proving. Keep track of how we read this. For all n in the integers.
Positive?
Now we have a plus up there, which means the positive integers.
Isn't that just the naturals?
No, the naturals include 0. This is 1, 2, 3, 4, 5, 6, 7, ... The naturals are 0, 1, 2, 3, 4, 5, 6, 7. So this is saying we're not including 0.
Okay.
So for all positive integers, n, 2 to the 0, plus 2 to the 1, plus 2 to the 2, plus 2 to the 3, plus ... 2 to the n minus 1, is equal to 2 to the n minus 1. Let's do a concrete example. Let's say n we pick to be 4. You can pick any positive integer n, and this holds. You can pick 1, 4, 7, 19, whatever you want. I'm going to just pick 4.
Okay.
So in that concrete case, what is it saying? It's saying 2 to the 0, plus 2 to the 1, plus 2 to the 2, plus 2 to the 3. Go all the way till we're 1 less than the number we're doing it for, in our case 4, is equal to 2 to the 4 minus 1.
Oh, yeah, this is one of our...
So let's see this happen. What is 2 to the 1? Or 2 to the 0, sorry. 1 plus 2 plus 4 plus 8. So what does 1 plus 2 plus 4 plus 8 equal? 15. What's 2 to the 4? 16 minus 1 is 15. Oh, it worked. Maybe it just happened to work that time. Maybe when you plug in 20 or 100 or 2,000 or 96,297,000, it stops working. We're going to prove that it always works, no matter what. You with me? And so we're going to give a counting proof of this. And in order to do a counting proof, we need to find something that our numbers can count.
Okay.
And then show that both sides of the equation count that thing. So find something that this could be counting, and show that this also counts it. Now, what do we know 2 to the n counts?
The power set of n.
It counts all the subsets of an n element set. If I have the set 1, 2, 3, how many subsets can we make of that set? 2 to the 3, or 8. Good? Counting subsets, that was a huge part of what we talked about last time. Had a whole section devoted to just counting subsets. So, what does 2 to the n minus 1 count? If 2 to the n counts an n element set, so 2 to the n counts all the subsets you can make of 1, 2, 3, dot, 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 all the way up to n. That's what 2 to the n counts, all the subsets you can make of this set. What does 2 to the n minus 1 count? What's something that could be counting?
All of that without the empty set.
All non-empty subsets. If this counts all the subsets, this could be counting all non-empty subsets. How many empty subsets are there of this set? One, just the empty set. That's the only empty subset of this set. Every other subset of this set has some elements in it. You with me? So, that's a good idea for what this can count. So then we have to come up with a way that this is counting the exact same thing. Okay? And so here's how I'm going to break it up. In our concrete example, I'm going to stick with n is 4 so I can write out all the sets and not hate my life. We're going to do a concrete example where n is 4. So we're looking at a set that has 4 elements in it. How many subsets does that set have? 16. How many non-empty subsets does it have? 15. So we see how this counts, all the non-empty subsets of that. Now let's see how this counts, all the non-empty subsets of it as well. Here's the way I'm going to break it up. I'm going to count all the non-empty subsets that have 1 as their max element, and then 2 as their max element, and then 3 as their max element, and then 4 as their max element.
What do you mean by max element?
So here's exactly what I'm looking at. So we're looking at the set A right here. I have all its subsets written out right here. And notice I structured them. Here's all the subsets of this set that have 1 as the biggest thing in them.
Oh, okay.
Here's all the subsets of this set that have 2 as the biggest thing in them. Here's all the ones that have 3 as the biggest thing in them. Here's all the ones that have 4 as the biggest thing in them.
Okay.
You with me so far? And now, just counting them, there's 1, or 2 to the 0, same thing. 2, or 2 to the 1. 4, or 2 to the 2. 8, or 2 to the 3. And so notice, in this very concrete example, it works. This plus this plus this plus this counts all the non-empty subsets of that set. Okay, now why is it following this pattern? So let's try and get some intuition for that. So imagine I'm going to count how many subsets I can make of the set, but I tell you I have to use 4. So whatever the set is, I tell you it for sure has 4 in there.
Okay.
How many subsets can I make that for sure have 4 in there? 8. How do you get that? Well, let's look at this set without 4 in it. What does it have? 1, 2, 3. Now pick any subset of this and add those elements to here. Or add 4 to it, but add those elements to here. And that gives you a subset where 4 is your max element. And so how many subsets of this set can I make? 8, or 2 to the 3. So 2 to the 3, notice ignore the 4 in all these sets. And what I'm left with is all the subsets of this. I took all the subsets of this and added 4. Let's see, one of the subsets of this is the empty set, add 4. There it is. One of the subsets of this is just 1, add 4. There it is. One of the subsets of this is just 2, add 4. There it is.
Yeah.
One of the subsets of this by itself is just 3, add 4. Sorry, I accidentally forgot that and plugged it later. Now we could have done 1, 2, add 4. 1, 3, add 4. 2, 3, add 4.
Right.
1, 2, 3, add 4. So all the subsets of this is the exact same thing as all the subsets of this with 4 as a max element. You see that? And so now we're just going to generalize that exact thinking in our counting proof. It's going to be the exact same concept. Our n here is going to be however big the set is, and our k is going to be a particular subset we're setting up, like 4. So let's read through it. Let n in the positive integers. Let n be any positive integer, 2, 5, whatever. Up here we did the concrete case of 4. And let a be the set 1, 2, 3, 4, dot, 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 up to whatever that n is. And it could be 100, 1,000, it could be 7, whatever it is. So that the size of A is equal to, how many things are in A? N things.
Okay.
So we've got a set of n elements here. The numbers 1 through n. Observe that since there are 2 to the n subsets of A, that's what we proved last week, then there are 2 to the n minus 1 non-empty subsets of A.
Wait, is that? Oh, okay.
So far I said 2 to the n minus 1 counts all the non-empty subsets of A.
Yep.
Now I'm going to show that 2 to the 0 plus 2 to the 1 plus 2 to the 2 dot 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 plus 2 to the n minus 1 also counts all the non-empty subsets of A. Okay. Now, consider the number of subsets of A that have k as a max element, where k is some number between 1 and n.
Including n.
Including n. So in our case, when I was writing that out up here, we used 4 for our k.
Yeah.
But we could have used 3 for our k. Let's redo the syncing with 3 for our k. If I said, let's pick 3 as our max element, how many subsets can we make where 3 is our max element? Well, we look at the set 1, 2, not including 3, take all the subsets of this, and then add 3 to it, and that gives me all the subsets with 3 as a max element. This has the empty set, add 3. This has 1, add 3. This has 2, add 3. This has 1, 2, add 3.
Right.
So our k here is some number between 1 and n, could be like that 3.
Right.
Such a subset has a form of dot 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 up to k, where the other elements are selected from 1, 2, 3 dot 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 up to k minus 1.
Yeah.
If the max element is k, then the only elements we can add to this set have to be smaller than whatever our k is. If our k is 3, then the elements we're adding to the set have to be smaller than 3. So they can go up to 3 minus 1 or 2 in that concrete case. So, read that one more again. Such a subset has a form of dot 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 up to k, where the other elements are selected from the set 1, 2, 3 up to k minus 1, because k has to be the max element. So all the other things we put in there have to be smaller than k. Now, how many subsets are there of 1, 2, 3 dot 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 all the way up to k minus 1? There are just 2 to the k minus 1, 2 to however many things are in that set. So since there are 2 to the k minus 1 subsets of 1, 2, 3 dot 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 up to k minus 1, then there are 2 to the k minus 1 ways of finishing the subset, this subset, dot 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 up to k, with k as its max element.
What do you mean by finishing?
Finishing, plugging in the elements for it. So it has this form. How do you plug in the elements to finish it off to get a subset with k as a max element?
Okay.
I didn't want to plug a bunch of union notation in here. I thought it might make a mess of it.
I see.
But could have been a bit more precise. Was afraid of losing you for the sake of precision. Okay, so since there's 2 to the k minus 1 subsets of this, and we're taking subsets of this and adding it to this set to get a subset with k as the max element, then there are 2 to the k minus 1 ways of finishing the subset with k as a max element.
Okay. Yep.
So then there are 2 to 0 with 1 as a max element, 2 to the 1 with 2 as a max element, dot dot dot, and 2 to the n minus 1 with n as a max element.
Yeah.
So since a non-empty subset of our initial set, 1, 2, 3, 4, 5, 6, 7, 8, all the way up to n, has to have a max element between 1 and n, then adding up all the max element subsets gives us a count of 2 to 0 plus 2 to the 1 plus 2 to the 2 dot 2 to the n minus 1, and counts all the non-empty subsets. Because every non-empty subset has to have a max element, because it has something in there. So, therefore, they both count the same thing. So, therefore, for all positive integers n, 2 to the 0 plus 2 to the 1 plus 2 to the 2, all the way up to 2 to the n minus 1 is equal to 2 to the n minus 1. There we go. That's the proof. Okay. The next one in the section, I'm not going to write out the full proof for you. I think it's an easier one to get. Here's what it's proving. We're going to prove that for all positive integers n, 1 times 1 factorial, plus 2 times 2 factorial, plus 3 times 3 factorial, dot, 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 plus n times n factorial, is equal to n plus 1 factorial minus 1. Now, it has scarier notation, so let's write out a concrete case. Pick some number n. In the concrete case here, I picked n to be 4. Or sorry, I picked it to be 3.
Okay.
So we're going to do 1 times 1 factorial plus 2 times 2 factorial plus 3 times 3 factorial is equal to 3 plus 1 is 4 factorial minus 1. Let's check that. What's 1 times 1 factorial? 1 plus 2 factorial is 2 factorial is 2 times 1.
Oh, it's 2.
2 times 2 is
Sorry.
4. What's 3 factorial? 3 factorial is 3 times 2 times 1. That's
6.
times 3 is
18.
18. Okay, so 18 plus 4 is 22 plus 1 is 23. And is that in fact equal to Let's see, what's 4 factorial? That's 4 times 3 times 2 times 1. 24 minus 1, which is equal to 23. It worked.
Okay.
Would it have worked if we went up to 4, if we went up to 5, if we went up to 10? The answer is yes, it would always work. Now we're going to give a counting proof of how this works. Now first off, what does n factorial count? Instantly, what should we think n factorial counts?
The number of ways of arranging a list of numbers.
The number of ways to arrange n elements in a list. So 4 factorial counts how many ways I can arrange 4 objects in a list. If I have objects 1, 2, 3, and 4, how many ways can I arrange them in a list?
4 factorial ways.
How many options do I have for which element comes first?
4.
4. And then once I choose that, how many options do I have for which element comes second?
4.
3, because we don't have repeats. Sorry, without repeats. If it was repeats, then we would have just done n to the 4, right?
Yes.
And then, once I pick that one, how many options do I have for what's left? 2. And then once I pick that, how many options do I have for what's left? 1. And so that's a total of 4 times 3 times 2 times 1, or in other words, a total of 24, or 4 factorial. In this concrete case, I wrote them all out right here. Here's all 24 ways you can write out a list of the numbers 1, 2, 3, 4. Good so far? So n factorial counts how many ways we can arrange n elements in a list.
Right.
So n plus 1 factorial here is counting how many ways we can arrange n plus 1 objects in a list. Good? Now, what could n plus 1 factorial minus 1 be counting?
Same thing minus the empty set.
Well, there is no empty set here, so n plus 1 factorial, pretend our concrete case n here is 3. So n plus 1 factorial, that's right here. That counts these. All the ways we can arrange 4 objects. Saying in our concrete case n equals 3. So this is counting all these lists. All the ways we can arrange 4 objects.
Minus 1.
Minus 1. What's the most natural one to eliminate if we have to eliminate one? 1, 2, 3, 4 is the most natural one to eliminate.
Yeah.
So now, in words, what is this counting?
All of the elements.
It's counting all the ordered lists we can make where we don't have 1 in the first position, and don't have 2 in the second position, and don't have 3 in the third position, and don't have 4 in the fourth position. And ... don't have Kate in the kth position. You with me?
Yeah.
Okay, so now we need to see how this is counting the exact same thing. This time, I'm going to count it backwards. I'm going to start with 3 times 3 factorial. Here's what I'm going to tell you. We're going to make a list of the numbers 1, 2, 3, 4. But I am not going to put a 1 in the first position. So if I'm not going to put a 1 in the first position, how many choices do I have for what goes here? 3. Now, I don't care what goes here.
No, I can't.
So how many options do I have left? I'm going to start by just counting how many don't have 1 in the first position.
Okay. It's 3.
So we don't have 1 in the first position. Now how many options do we have for what goes here? 3. How many for here? 2. How many for here? 1.
Okay.
So 3 times 3 factorial is how many don't have 1 in the first position.
Oh, 6.
So 1 not in the first position was equal to 3 times 3 factorial. Now let's count how many don't have 1 in the first position now how many do have 1 in the first position, but don't have a 1 in the second position.
Oh, the 2 there.
So we've got a 1 in the first position, we don't have a 2 in the second position. So how many options do I have for what goes here?
3.
If it can't be 2,
You have 2.
Oh, 2.
3 and 4. So we have 2 options for what goes here, and now times 2 for what's left, and then 1.
Yes.
So we have 1 in the first position, but not 2 in the second position, is equal to 2 times 2 factorial. And then finally, 1 in the first position, 2 in the second position, and we don't have 3 in the third position. How many options do I have for what goes here? 1 times 1 left, or 1 factorial.
That's 6.
And then, how many have 1 in the first position, 2 in the second position, 3 in the third position, but don't have 4 in the fourth position? None. And so now you just do that in a more generic way using your K's and filling it out that way. Make sense? Thought counting list was easier than counting subset, so decided to write out the subset one, not the list one. Okay, that is it for that. Test next week. Test next week.
Okay.
Don't miss it. Test next week.